11,400. That is how many years this world needs to complete a single journey around the sun. The last time it passed through this part of the solar system, human civilization had not yet invented writing. It is making that visit only once in our lifetime. When it leaves again, it will not return for another 11,400 years. In 2003, astronomers studying distant survey images noticed a tiny point of light moving so slowly that the first orbital calculations seemed impossible. The numbers were checked again and again. The result never changed. The object was not drifting through the familiar frontier beyond Neptune. It occupied a region where no known planet should have been able to place it. Its path carries it from 76 astronomical units from the Sun to nearly 936 astronomical units, wandering through a gravitational wilderness that current models of the solar system struggle to explain. It is also one of the reddest worlds ever discovered. Its day lasts roughly 10 Earth days, unusually slow for an object of its size, hinting that something unseen may once have been orbiting beside it. Some astronomers believe its strange path is the scar left by a passing star billions of years ago. Others suspect the gravity of an undiscovered planet still lurking in the darkness beyond Neptune. Neither explanation has been proven. Both remain among the biggest unresolved questions in planetary science. The world is called Sedna, named after the Inuit goddess cast into the freezing sea, whose story begins with isolation and ends in mystery. And perhaps the most remarkable fact of all is that our civilization has arrived at exactly the right moment to study it. This is the closest Sedna will come to the Sun for another 11,000 years. If space content like this is your thing, we've got plenty more. Subscribe and you'll have a new documentary waiting for you next time you need one. Let's talk about what we actually know. Imagine placing the same patch of sky under a microscope night after night. At first, nothing seems different. The stars hold their familiar positions, forming a dependable backdrop that barely changes across a human lifetime. Yet if you compare those images with enough patience, one tiny point may have drifted ever so slightly. That almost imperceptible movement is how we discover worlds far beyond the reach of ordinary sight. Sedna emerged through exactly this kind of search. Mike Brown and his colleagues were carrying out a systematic survey of the distant solar system using the 48-inch Samuel Oschin telescope at Palomar Observatory in California. Their approach depended on repeated observations rather than dramatic discoveries. Computer software compared photographs taken on different nights, searching for any faint object that shifted against the fixed pattern of distant stars. A genuine member of our solar system would move. Everything much farther away would remain almost unchanged. You might expect a distant object to be easier to notice because it covers such an enormous orbit. The opposite proved true. Sedna crossed the sky at only about 1 3/4 arcseconds each hour, an angle so tiny that it was almost indistinguishable from the background. Had its motion been even slightly slower, it could easily have escaped detection within the survey data. To understand where Sedna lives, astronomers rely on a special measuring stick called the astronomical unit. 1 astronomical unit equals the average distance between Earth and the Sun, about 93 million miles. Instead of counting ordinary miles across the solar system, this larger unit lets us describe immense distances with greater clarity. Sedna travels from about 76 astronomical units at its nearest point to roughly 936 astronomical units at its farthest, carrying it across a span that dwarfs the orbits of the familiar planets. Brightness presents another challenge. Sedna shines at magnitude 21, making it roughly 100,000 times too faint for human eyes alone. Detecting something so dim required highly sensitive charge, coupled device cameras, electronic detectors capable of recording individual packets of light that had reflected from Sedna after traveling billions of miles through space. Every captured photon added another tiny piece to a picture that no single glance could reveal. Before Sedna appeared, the Kuiper Belt marked the accepted frontier of the planetary system. This broad collection of icy bodies extends from about 30 to 50 astronomical units beyond the Sun and includes Pluto, along with countless smaller worlds. Sedna does not belong there. Even at its closest approach, it remains far beyond the Kuiper Belt's outer edge, occupying a region that had no recognized population when it was first discovered. Far beyond that lies the proposed Oort cloud, a vast spherical reservoir of icy bodies thought to begin around 2,000 astronomical units from the Sun and extend much farther into surrounding space. Sedna does not belong there either. We find it suspended between these two regions, occupying a stretch of the solar system where existing formation models predicted almost nothing should remain. That unexpected location transformed one distant object into evidence that the map of our own cosmic neighborhood was still incomplete. Picture a single thread stretched across the solar system, looping outward so far that it almost seems to belong to another star. That thread is Sedna's orbit, and every point along it preserves a record of ancient gravitational events. When astronomers finished calculating its path, they realized they were looking at something that fit nowhere within the accepted picture of how our planetary neighborhood came to be. Sedna approaches the Sun no closer than 76 astronomical units. At its greatest distance, it reaches roughly 936 astronomical units before beginning the long return. Among known objects bound to our Sun, very few travel along an orbit this elongated. Even at its nearest approach, Sedna remains about 2.5 times farther from the Sun than Neptune, the outermost recognized planet. You never find it wandering into the familiar territory occupied by the giant planets. Its calendar unfolds on an entirely different scale. One Sedna year lasts about 11,400 Earth years. During that span, entire civilizations can appear, flourish, disappear, and give way to new cultures before Sedna completes one leisurely circuit around the Sun. Human history becomes a brief moment within a single season of its journey. This unusual path created a genuine problem for planetary science. The standard models describing the early solar system predicted that objects scattered into such distant regions should experience repeated gravitational encounters with the giant planets. Those encounters generally produce two outcomes. A smaller body is pushed inward toward the broader population beyond Neptune, or it gains enough energy to leave the solar system forever. Remaining in a long lasting orbit like Sedna's was not expected. To understand why, we can imagine the earliest solar system as a place filled with moving debris, while the giant planets continued growing. Jupiter and Saturn became enormously influential because of their immense mass. Their gravity redirected countless icy bodies, changing speeds and directions with every close encounter. Over millions of years, they acted like celestial bulldozers, clearing pathways, scattering material, and reshaping the architecture of the young solar system. A world the size of Sedna should have been swept into one of those familiar outcomes. But another detail refuses to cooperate. Sedna never comes close enough to Neptune for Neptune's gravity to explain its orbit. Many distant icy worlds owe their unusual paths to repeated interactions with that planet. Sedna remains well beyond Neptune's strongest reach, leaving astronomers without the mechanism they normally depend upon. When those orbital calculations were confirmed during 2003, the discovery became more than the addition of another distant object. It challenged the prevailing framework used to explain the formation of the outer solar system. Any successful model would now have to account for Sedna without ignoring the precise measurements that revealed its remarkable path. Two broad possibilities gradually emerged from that puzzle. Did another star brush past the newborn sun long ago, gently reshaping distant orbits before disappearing into the Milky Way? Or does an undiscovered planet still travel far beyond Neptune, guiding Sedna through an influence too subtle to notice anywhere else? At present, both ideas remain scientifically active, carefully studied, and still awaiting the evidence needed to settle the story. Long before the sun became the steady center of our familiar planetary family, it probably belonged to a much larger gathering. If you could travel back across those immense ages, you would not find our star shining alone. You would see hundreds, perhaps thousands, of young stars forming together inside a vast stellar nursery, a birthplace where gravity gathered gas and dust into countless newborn suns, sharing the same corner of the galaxy. Within such crowded surroundings, neighboring stars occasionally passed much closer to one another than they do today. Astronomers believe this early environment may hold the key to Sedna's remarkable journey. Around 4 billion years ago, one of those neighboring stars may have drifted to within roughly 800 astronomical units of the young Sunday. That sounds unimaginably distant. Yet, on the scale of a stellar nursery, it was close enough for gravity to reach deep into the outer edge of the developing solar system. The encounter would not have resembled a collision. Instead, it unfolded as an extended gravitational conversation lasting thousands of years. As the visiting star continued along its own path, its gravity gently pulled on distant icy bodies circling the Sunday. Some objects may have been nudged into long, stretched orbits while remaining securely bound to our star. Others likely continued almost unchanged. Sedna could be one of the survivors carrying the signature of that ancient meeting. This idea gained considerable support in 2004 when planetary scientists Alessandro Morbidelli and Harold Levison performed detailed computer simulations. Their virtual solar systems recreated close stellar flybys within young star clusters. Under the right conditions, those calculations naturally produced distant objects traveling along paths strikingly similar to Sedna's. One requirement stood out. The sun needed to remain inside its birth cluster for several million years before the surrounding stars gradually dispersed throughout the Milky Way. That possibility gives Sedna an entirely different role in our story. We usually think of distant icy worlds as leftovers from planet formation. Here, you can imagine something more subtle. Sedna may preserve evidence of the neighborhood where the sun itself was born. Its orbit becomes a surviving record from an era when our star still shared space with siblings that have long since wandered away. The hypothesis also makes a prediction. If one passing star reshaped the distant solar system, Sedna should not be unique. We would expect many similar bodies occupying related orbits far beyond the Kuiper belt. Astronomers often describe this hidden population as the inner Oort cloud, a region that bridges familiar territory and the far greater cloud believed to surround the entire solar system. Every newly discovered object helps refine the geometry of that ancient encounter, revealing another small piece of an event preserved only through gravity. Even the visitor's speed appears surprisingly modest. Researchers estimate the passing star may have traveled at only about 1/2 mile per second relative to the Sunday. By galactic standards, that was an unhurried passage. giving gravity enough time to reshape distant orbits without tearing the young solar system apart. Today, that neighboring star has vanished into the vast stellar population of the Milky Way. After billions of years of motion, identifying it has become essentially impossible. Yet its fingerprints may still circle our Sun, traced into Sedna's graceful orbit with remarkable persistence, waiting for us to recognize the story written there. Some discoveries begin with a telescope pointed toward a distant light. Others begin with a pattern that refuses to disappear. Planet 9 belongs to the second kind. No one has photographed this proposed world, yet its possible presence emerged from the graceful motions of objects already known, each tracing an orbit that seemed to share an unexpected relationship with the others. The modern hypothesis took shape during 2016 when Konstantin Batygin and Mike Brown studied six extreme trans-Neptunian objects, including Sedna. Rather than focusing on where these distant bodies were located, they examined the orientation of their orbits through space. Those orbital elements, the mathematical descriptions defining the size, shape, and direction of an orbit, appeared clustered in a way that ordinary chance struggled to explain. The pattern suggested that something large might be guiding them over immense spans of time. Their statistical analysis produced an intriguing result. The probability that all six objects would display this arrangement by coincidence was estimated at only about 0.007%, less than one chance in 14,000. Statistics alone cannot reveal an unseen planet, yet they can point toward hidden influences that deserve careful investigation. In this case, gravity became the leading suspect. If Planet 9 exists, researchers estimate it could contain between 5 and 10 times Earth's mass, while circling the Sun at distances ranging from roughly 400 to 800 astronomical units. That places it about 20 times farther from the Sun than Neptune. At such an extraordinary distance, sunlight becomes remarkably weak, leaving the planet only a tiny fraction as bright as familiar worlds. Even the largest telescopes could overlook an object so faint if it happened to occupy the wrong region of the sky. Its own journey would unfold with extraordinary patience. One complete orbit may require anywhere from 10,000 to 20,000 years. Every civilization that has ever observed the heavens occupies only a brief instant within that immense cycle. As you imagine such a world moving across the darkness, it becomes easier to understand why direct detection has proven so difficult. Planet 9 offers more than a possible explanation for Sedna. Computer models suggest its gravity could also account for several other unusual features scattered across the distant solar system. Some extreme objects follow unexpectedly tilted paths, while the Sun itself rotates at an angle of about 6 degrees relative to the primary plane of the planets. Individually, these mysteries remain incomplete. Together they form a collection of clues that seem willing to share a common explanation. We are now entering a period when that possibility can be tested more thoroughly than ever before. The Vera C. Rubin Observatory in Chile is surveying the sky with exceptional depth, repeatedly imaging vast regions to uncover faint moving objects beyond Neptune. Its observations are expected to reveal many previously unknown members of the outer solar system, while steadily narrowing the places where Planet 9 could still remain concealed. If that distant world is eventually found, it will become the first new planet discovered in our solar system since Neptune in 1846. You would be witnessing a discovery made through gravity before light, where the paths of remote icy worlds revealed an unseen companion long before any telescope could finally capture its faint glow. Color is often the first clue a distant world offers. Before we can touch its surface or map its landscape, we measure the light it reflects. In Sedna's case, that light carries an unmistakable signature. Among the countless icy bodies beyond Neptune, very few appear as deeply red. Even compared with the richest crimson members of the Kuiper belt, Sedna stands near the extreme end of the scale, as though billions of years have slowly painted its surface with an ancient stain. You might instinctively compare that color with Mars. The resemblance ends almost immediately. Mars owes its familiar appearance to iron oxide, the same chemical process that produces rust on Earth. Sedna's surface tells a completely different chemical story, one unfolding in temperatures and conditions unlike anything found on the rocky planets. The leading explanation centers on substances known as tholins. The name describes a family of complex organic molecules created when simple ingredients, including methane, ethane, and nitrogen, are exposed to energetic ultraviolet light from the sunday. Over immense spans of time, that radiation breaks ordinary molecules apart and allows their fragments to reconnect into increasingly complicated structures. The resulting material develops a rich reddish-brown appearance, gradually coating the frozen landscape grain by grain. Scientists first produced these compounds in a laboratory during 1979. Carl Sagan and Bishan Kare recreated the harsh environment of deep space by exposing simple gases to energetic radiation. Instead of remaining unchanged, the gases transformed into sticky reddish material unlike the ingredients that formed it. They named these new substances tholins, borrowing a Greek word meaning muddy. Their experiments suggested that the chemistry shaping distant icy worlds could emerge naturally without requiring life or volcanic activity. Sedna provides one of the most favorable settings for this process. Its surface temperature hovers near minus 400 degrees Fahrenheit, making it one of the coldest environments ever measured within the solar system. At such temperatures, chemical reactions proceed with extraordinary patience. Molecules move very little. Ice remains locked in place. Layer after layer of radiation-driven chemistry can accumulate across unimaginable lengths of time. That persistence may be the real reason Sedna appears so unusually red. Unlike many other worlds, it shows little evidence that fresh material has repeatedly reached the surface. Large impacts appear uncommon. No convincing signs point toward active volcanism. There is no known geological process, regularly exposing brighter ice beneath the aging exterior. The reddish coating may therefore represent billions of years of uninterrupted chemical change, preserved almost exactly where it formed. As we observe Sedna from across the darkness, we are seeing more than a color. We are looking at chemistry that may have begun before the planets finished assembling around the young Sunday. Those complex organic materials have endured through nearly the entire history of the solar system, remaining exposed beneath faint sunlight, while continents formed on Earth and life gradually transformed our own world. Sedna's surface may be one of the oldest surviving chemical archives, still orbiting the Sun, preserving ingredients that have changed remarkably little since the earliest chapter of our cosmic neighborhood. Every world introduces itself through light. We cannot hold a fragment of Sedna in our hands or examine its frozen plains up close, yet every ray reflected toward Earth carries subtle clues about the materials resting across its surface. By separating that light into its individual wavelengths, astronomers perform a technique called spectroscopy, a method that reveals what a distant object absorbs and reflects. The resulting pattern becomes a chemical signature written into the light itself. Those signatures indicate that Sedna's exterior contains frozen methane, frozen water ice, and frozen nitrogen. Each substance absorbs specific wavelengths while reflecting others, allowing researchers to identify them despite the enormous distance. We never see these materials directly. Instead, we recognize them through the faint fingerprints they leave behind in the reflected sunlight reaching our telescopes. The proportions of those frozen compounds make Sedna especially intriguing. Pluto contains many of the same ingredients. Eris does as well, and Triton shares several similarities despite orbiting Neptune instead of the Sunday. Yet Sedna combines these ices in noticeably different amounts. Like a unique fingerprint distinguishing one individual from another, its surface chemistry separates it from every other large icy world studied so far. That difference hints that Sedna followed its own path through the earliest history of the solar system. Its interior remains hidden from direct observation, although scientists can estimate what lies beneath the frozen exterior. By combining Sedna's size, its estimated density, and computer models describing how icy worlds evolve, researchers conclude that it is probably differentiated. In simple terms, that means heavier rocky material gradually settled toward the center, while lighter frozen substances remained closer to the surface. Gravity quietly sorted those ingredients during Sedna's earliest years, creating internal layers that have likely remained stable ever since. What makes this particularly fascinating is the origin of those materials. Sedna formed within the same protoplanetary disk, the broad rotating cloud of gas and dust surrounding the young sun that also produced Earth and every other planet. The atoms making up Sedna were once mixed with the same primordial material that eventually became mountains, oceans, and living creatures here at home. Our worlds began together before taking dramatically different journeys through time. Temperature shaped those journeys in profoundly different ways. Earth experienced volcanic activity, flowing water, atmospheric weather, and constant geological recycling. Sedna remained in an environment of relentless cold, preserving much of its original composition beneath a frozen crust. While our planet continuously transformed its surface, Sedna spent billions of years protecting ancient materials from widespread alteration. Among those preserved materials are likely complex prebiotic organic molecules. These substances are not living organisms, nor do they represent evidence of life. Instead, they are the chemical building blocks that can contribute to life when conditions become favorable. In laboratories on Earth, similar compounds have demonstrated remarkable chemical potential, making Sedna an especially valuable natural archive of the organic inventory present during the solar system's infancy. Everything we know about this distant world comes from light alone. No spacecraft has crossed the immense gulf separating us from Sedna. Every conclusion about its composition has been drawn through patient observations made by ground-based observatories and telescopes orbiting above Earth's atmosphere. Across billions of miles, reflected sunlight continues carrying fragments of Sedna's story, allowing us to study a world that has remained almost untouched since the earliest days of our cosmic neighborhood. Scale often hides behind familiar names, so let us leave labels aside for a moment and picture the world itself. Sedna stretches only about 620 miles across, comparable to the distance between Los Angeles and Portland, Oregon. Compared with the giant planets, that seems remarkably modest. Even beside several of its icy neighbors, Sedna occupies a smaller place than many people imagine. Yet size alone tells only part of its story. A body does not need to rival a planet before gravity begins reshaping it. Once enough material gathers together, its own weight slowly pulls sharp edges inward until a rounded form emerges. Astronomers regard that transition as one of the defining characteristics of a dwarf planet. Sedna appears large enough for gravity to have completed that work, producing a nearly spherical world rather than an irregular chunk of frozen rock. Even so, the International Astronomical Union has never formally voted on Sedna's official classification, leaving it in a curious scientific category where evidence points one way while terminology waits behind. We can appreciate that scale more clearly beside familiar companions. Pluto measures roughly 1,477 miles across, giving it well over twice Sedna's width. Eris, considered the most massive known dwarf planet, spans about 1,445 miles. Both worlds comfortably exceed Sedna in size, although each shares the same distant realm of frozen sunlight and ancient ice. Distance creates another challenge. Although modern observatories are astonishingly capable, Sedna remains so remote that every image we possess reduces it to a single unresolved point of light. No mountain, crater, ridge, or frozen plain can yet be distinguished. Every surface detail remains blended into one tiny dot, leaving astronomers to infer its characteristics from the faint light reflected across the immense darkness separating it from us. Even that tiny world possesses remarkable breadth. Its total surface covers roughly 1,200,000 square miles, slightly larger than the combined land area of Alaska, Texas, California, Montana, and New Mexico. That comparison reminds us how easily the word small can become misleading. A world can seem modest beside planets, while still offering a landscape vast beyond ordinary human experience. Imagine standing there for a moment. You would lift your eyes and search for the sun that shaped every chapter of our solar system. Instead of a brilliant disk dominating the sky, you would find what appears to be an exceptionally bright star. Its light would deliver only about 1/8,500th of the sunlight reaching Earth, leaving the landscape illuminated by a distant beacon that barely outshines the brightest stars visible from our own planet. Look outward across the frozen ground, and another subtle difference emerges. Because Sedna is comparatively small, its horizon would seem unexpectedly close. At ordinary human height, you would notice the world curving away after only a short distance, gently revealing the shape of the sphere beneath your feet, while the immense darkness above stretches almost without end. Some mysteries reveal themselves through what we discover, others persist because something expected never appears at all. As astronomers continued studying Sedna after its discovery, one of their earliest questions centered on a remarkably familiar expectation. Where was its moon? You can understand why that assumption seemed almost unavoidable. Pluto has Charon. Eris is accompanied by Dysnomia. Haumea is orbited by Namaka and Hyakka. Across the distant reaches of the outer solar system, companion worlds appear so frequently that they almost feel like part of the natural architecture of these icy bodies. Sedna seemed destined to join that pattern, and the search began with one of humanity's most capable eyes, the Hubble Space Telescope. The observations were thorough. Every image was examined for a faint point of light moving alongside Sedna. Astronomers expected to see a tiny companion tracing a graceful orbit. Instead, the images showed only Sedna itself. No moon emerged from the surrounding darkness. If a companion exists, it is probably smaller than about 60 miles across, exceptionally dark, or positioned so close to Sedna that even the Hubble Space Telescope could not separate the two objects. At first glance, that absence might seem like an interesting detail rather than a genuine scientific problem, but another measurement changes the picture entirely. Sedna turns very slowly. One complete rotation takes about 10 Earth days. Compared with many similarly sized bodies beyond Neptune, that pace is unusually leisurely. Most rotate much faster, completing a full spin in only several hours. Why does that matter to us? Because astronomers often connect slow rotation with an invisible exchange of energy between a world and its companion. Over immense spans of time, the gravity of a moon gently pulls on its parent body. Those repeated tugs gradually redistribute angular momentum, the quantity describing an object's rotation. Bit by bit, the spin becomes slower until a stable rhythm develops between both worlds. Across the outer solar system, that explanation has successfully described several familiar systems. But Sedna refuses to cooperate. We observe the slow rotation expected from billions of years of tidal interaction, yet the companion responsible for those tides has never been found. The evidence seems to point toward a partner that remains hidden. Other possibilities have been proposed. Perhaps Sedna formed with an unusually slow spin from the beginning, preserving that ancient motion throughout its long history. Another suggestion imagines a powerful collision that altered its rotation billions of years ago. Both ideas remain physically possible, yet neither explains the broader pattern as naturally as a long lasting relationship with an orbiting moon. That leaves one intriguing possibility still waiting in the darkness. Sedna may possess a remarkably small companion, coated with material dark enough to reflect very little sunlight. Such a moon could remain concealed within Sedna's own glow, escaping even the remarkable vision of the Hubble Space Telescope. Future observatories with sharper angular resolution may finally separate those two faint points of light. Until then, even the simple question of how this distant world came to spin so slowly remains unanswered, reminding us that Sedna still guards some of its most basic history. A name can change the way we remember a distant world. Long before its surface could be understood in greater detail, before its unusual orbit inspired new theories, this remote object received a name that carried a story far older than modern astronomy. On March 15th, 2004, Mike Brown and his colleagues officially announced their discovery and introduced the world as Sedna. The choice followed a tradition established by the International Astronomical Union. Objects traveling on orbits like Sedna's are generally named after figures connected with creation stories, extreme cold, or realms beyond ordinary human experience. Among the many possibilities, Sedna seemed to belong naturally. The name echoed both the environment where the object spends its endless journey and the extraordinary isolation that had already become part of its scientific identity. As we follow that name back to its origins, we arrive in the rich traditions of the Inuit people. Sedna appears as a powerful young woman whose story has been told in several forms across the Arctic. In one widely shared version, she is cast into the freezing ocean by her own father. As she struggles to hold onto the side of the boat, her fingers are cut away. Those severed fingers sink beneath the waves and transform into seals, walruses, and whales, becoming the living creatures that sustain Arctic communities. From beneath the icy sea, Sedna herself becomes a guardian whose influence reaches every hunt and every season. You can sense why astronomers found such a connection meaningful. The newly discovered world also exists far beyond familiar places, separated from the crowded family of planets by astonishing distances. Its path carries it into one of the coldest known regions associated with our solar system, where sunlight grows faint and time unfolds at an almost unimaginable pace. The mythology was never intended as a scientific explanation, yet the symbolism settled beside the discovery with remarkable harmony. Another possibility briefly entered the discussion. The team considered Persephone, the Greek goddess associated with the underworld. That choice could not be used because another asteroid had already received the name. The search continued until Sedna emerged as the clear favorite, offering both cultural significance and a connection to a frozen realm unlike any other. Mike Brown later reflected that the decision felt appropriate for reasons extending beyond official naming rules. Here was a world lingering near the edge of everything we commonly recognize, carrying an Inuit name rooted in landscapes defined by enduring cold. The association seemed to acknowledge both the object's physical environment and the human traditions that have long understood the power of frozen places. Alongside its familiar name, Sedna also carries a numerical identity. It bears the provisional number 90,377, marking it as the 90,377th minor planet to receive official numbering. That designation may eventually change if the International Astronomical Union formally recognizes Sedna as a dwarf planet. Until then, both names remain part of its story, one expressing the careful order of astronomy, the other preserving an ancient legend that now travels through the darkness beside a world at the farthest frontier of the sun's domain. Long before the world learned Sedna's name, its existence rested inside a handful of faint images gathered beneath the California sky. On the night of November 14th, 2003, the Samuel Oschin telescope recorded a tiny point of light that seemed almost indistinguishable from countless distant stars. Nothing in that first image alone proved a new world had been found. We would need patience before certainty could emerge. Finding distant objects requires more than taking a single photograph. Astronomers compare images captured over multiple nights, searching for points of light that drift against the apparently fixed background of stars. A genuine member of our solar system changes position, even if only by the smallest amount. A background galaxy does not. An imaging defect remains exactly where it first appeared. Only careful comparison reveals which tiny speck is truly traveling through space. Mike Brown's search software had been designed specifically for that challenge. After processing countless survey images, the program highlighted one unusually slow-moving candidate. Computers can recognize patterns with remarkable consistency, yet they cannot replace scientific judgment. Brown and his colleagues examined the evidence themselves, confirming that the faint signal represented a real object rather than an imaging artifact or statistical mistake. By then, the team had already devoted more than a year to a systematic exploration beyond the Kuiper Belt. Their search had produced important discoveries, including Quaoar and several other distant members of the outer solar system. Every new observation expanded the map a little farther. Sedna first appeared to be another promising addition, but the calculations soon suggested something altogether different. As additional observations accumulated, Brown determined the object's orbit. The result refused to resemble anything expected. Rather than tracing a path similar to previously known distant worlds, Sedna followed an astonishingly elongated journey unlike any orbit measured within the solar system at that time. Brown later explained that he repeated the calculations several times because the numbers seemed almost impossible to accept. Would you trust such an extraordinary result after seeing it only once? His reaction was unexpectedly restrained. Instead of immediate celebration, Brown described experiencing a cold feeling. The emotion came from recognizing that the mathematics remained consistent while existing theories struggled to explain what they revealed. Every repeated calculation returned the same remarkable answer. The discovery itself was becoming increasingly difficult to question, but the team resisted, announcing their findings immediately. Additional months were devoted to gathering more observations, refining the orbital solution and testing every reasonable possibility that an error had slipped into the analysis. Scientific confidence grows through repeated verification, especially when a result challenges long accepted ideas. Only after that careful process did the announcement arrive on March 15th, 2004. The news quickly attracted international attention. National Aeronautics and Space Administration Administrator Sean O'Keefe described the discovery as mind boggling, reflecting the extraordinary implications of a world occupying such an unexpected place. Before Sedna became a symbol of unanswered questions, it was simply a faint moving point that refused to fit comfortably within everything astronomers believed they already understood. Sometimes a discovery does more than add another object to a catalog. It quietly redraws the map itself. As astronomers continued tracing Sedna's remarkable path, they realized the familiar structure of the solar system no longer told the complete story. Between two well-known regions lay an unexpected realm that had received very little attention because almost nothing was known to exist there. Today, that distant territory is often described as the inner Oort cloud or the extended scattered disk. The exact boundaries remain subjects of continuing research, yet the region stretches from roughly 50 astronomical units to about 1,500 astronomical units from the Sunday. It occupies the enormous expanse beyond the Kuiper belt while remaining well inside the vast outer reservoir known as the true Oort cloud. Before Sedna appeared, many astronomers assumed this immense volume of space contained very little. The true Oort cloud lies even farther away. Current models place its inner edge near 2,000 astronomical units, with its outer reaches possibly extending to 100,000 astronomical units. At those astonishing distances, the Sun's gravitational hold becomes remarkably delicate. Objects there may require millions of years to complete a single orbit, drifting through space so slowly that neighboring stars can gradually influence their paths. Sedna belongs to neither neighborhood. Its closest approach to the Sun remains far beyond Neptune's influence, preventing it from fitting naturally within the Kuiper belt. Yet its orbit never stretches far enough to enter the true Oort cloud. We find ourselves looking at a world suspended between two established populations, occupying a region that earlier models left almost entirely unaccounted for. That unusual position transformed Sedna from an interesting discovery into evidence that the solar system contained an overlooked chapter. For several years, Sedna stood alone. Some wondered whether it represented an extraordinary accident, a solitary survivor of an ancient event that would never be repeated. But another clue eventually emerged. In 2018, astronomers confirmed the discovery of another distant body with a remarkably similar orbital style. Officially designated 2012 Victor Papa 113 and informally nicknamed Biden by its discoverers, Scott Shepard and Chad Trujillo, this object followed a path sharing many of Sedna's defining characteristics. Its closest approach to the Sun occurs near 80 astronomical units, and one complete orbit requires roughly 4,000 years. Those details differ from Sedna's own journey, yet both worlds clearly belong to the same extraordinary population. Rather than revealing identical histories, their differences hint that several processes may have shaped this distant realm over billions of years. As additional evidence accumulates, astronomers increasingly suspect that Sedna and its companion represent only the brightest members of a much larger family. Hundreds, perhaps even thousands, of similar objects may inhabit this remote frontier, remaining beyond the reach of today's instruments because they reflect so little sunlight across such overwhelming distances. We encountered Sedna only because its long orbit happened to carry it close enough for modern telescopes to notice. at precisely the fortunate moment when humanity had finally learned where to look. Our picture of the distant solar system remains surprisingly incomplete, even after decades of increasingly sophisticated observations. That uncertainty does not arise from a lack of effort. Instead, it reflects the immense challenge of finding worlds that spend nearly all their existence far beyond the reach of ordinary surveys. Distance, size, and orbital motion combine to hide them with remarkable efficiency, leaving enormous stretches of space that have barely been explored. At its present distance of about 84 astronomical units, Sedna receives only a tiny fraction of the sunlight that reaches Earth. Its dark, reddish surface reflects merely about 0.32% of the light falling upon it. Most of that already weakened sunlight continues into space rather than returning toward our telescopes. Against the darkness surrounding it, Sedna becomes little more than an exceptionally faint point, almost indistinguishable from countless distant stars. That faintness creates another obstacle. Objects at Sedna's current distance appear roughly 100,000 times dimmer than the faintest objects visible to the unaided human eye. Detecting them demands large aperture telescopes capable of gathering precious light, lengthy exposures that accumulate tiny numbers of arriving photons, and sophisticated computer software designed to recognize motion smaller than a single picture element across observations taken on different nights. Motion itself becomes part of the challenge. Many astronomical surveys are optimized to discover asteroids or ordinary Kuiper Belt objects, both of which drift across the sky quickly enough for automated systems to recognize with relative ease. Sedna barely seems to move at all. Without algorithms specifically designed to identify such gradual changes, an object like this can disappear into ordinary background noise, overlooked despite being present in the data. A new generation of observations promises to change that picture. The Vera C. Rubin Observatory is carrying out the legacy survey of space and time, repeatedly imaging the accessible southern sky every 3 nights over a period of 10 years. By reaching far fainter limits than previous wide-field surveys, it should uncover hundreds of additional objects inhabiting the extreme outer solar system, expanding a sample that has remained frustratingly small. Those discoveries will matter for reasons extending beyond simple numbers. As the population grows, astronomers will measure how these distant worlds are distributed through space and compare that pattern with competing models. Does the evidence preserve the signature of an ancient stellar encounter? Does it reveal the gravitational influence of an undiscovered massive planet? Or will the observations reject both ideas and require an explanation that no one has yet imagined? Even the scarcity of confirmed Sedna-like worlds carries meaning. After more than 20 years of dedicated searching, only Sedna and the object officially designated 2012, Victor Papa 113, clearly occupy this unusual category. That sparse population places meaningful limits on how closely another star could have approached the young sun, narrowing the history written across the most remote frontier of our planetary neighborhood. Imagine standing where daylight itself has almost reached its limit. Even at local noon, Sedna receives so little sunlight that the familiar warmth of our own world becomes almost impossible to imagine. With a surface temperature near minus 400 degrees Fahrenheit, this distant world ranks among the coldest environments ever measured anywhere in our solar system, preserving conditions that have changed remarkably little since its earliest history. Cold reshapes the behavior of matter. Substances that drift through Earth's air as invisible gases become solid here instead. Nitrogen freezes into surface deposits. Methane hardens into ice. Carbon monoxide also exists as a frozen material, settled across the landscape or forming delicate layers of frost that remain in place for extraordinary spans of time. What feels ordinary beneath Earth's skies becomes completely transformed beneath Sedna's distant Sunday. You might expect a world covered with frozen materials to possess a thin atmosphere hovering above its surface, but gravity tells a different story. Sedna is simply too small to hold a substantial blanket of gas around itself. Any volatile material, meaning compounds that can easily change from solid to gas, escapes once it leaves the surface. At such an immense distance from the sun, even the rare moments of sublimation, when frozen material changes directly into vapor, cannot build an enduring atmosphere before those particles drift away into surrounding space. Without an atmosphere, the landscape remains untouched by weather. No breeze crosses the plains, no clouds gather overhead, no rainfall, snowfall, or drifting mist alters the terrain. Sedna also appears to lack a moon, removing another source of gravitational influence that might otherwise stir its surface over immense stretches of time. Geological activity has never been observed there either. Instead, the terrain seems to rest beneath an environment shaped by extraordinary patience rather than continual change. Yet the surface is far from isolated. Throughout every hour of every age, cosmic rays stream inward from beyond our solar system. These are extremely energetic particles, traveling across the galaxy at tremendous speeds before striking Sedna's frozen crust. They penetrate several inches beneath the surface, breaking apart simple molecules and allowing new, increasingly complex organic compounds to form. Over billions of years, this persistent chemical processing gradually deepens the reddish coloration that distinguishes Sedna from nearly every other distant world. The light itself becomes difficult to picture. At roughly 84 astronomical units from the Sun, only about 1/7,000th of the sunlight reaching Earth arrives at Sedna. Even when the Sun stands highest above the horizon, it resembles an exceptionally brilliant star rather than the broad, glowing disk familiar to you and me. Midday there would remain darker than a moonlit night on Earth. Time also unfolds differently. Sedna completes one rotation in about 10 Earth days, allowing that faint daylight to linger across the landscape before yielding to another equally long interval of darkness. Together, they create an environment where chemistry advances almost imperceptibly, preserving a frozen record that has endured since the earliest chapters of our solar system. Long before any spacecraft begins such a journey, the voyage must first exist as mathematics. Engineers trace possible paths through the solar system years before metal is shaped or instruments are assembled. Sedna has inspired exactly that kind of careful planning. Mission studies conducted by the National Aeronautics and Space Administration and the European Space Agency have explored possible flyby missions, although none has received funding or advanced into a formally approved mission as of the middle of the 2020s. With today's propulsion technology, reaching Sedna would require extraordinary patience. A direct flight is expected to last roughly 24 to 30 years, depending upon the chosen trajectory and launch conditions. Even that remarkable journey would exceed the travel time of the New Horizons mission, which departed Earth in 2006 and reached Pluto during 2015 after about 9.5 years of flight. But Sedna presents a challenge that Pluto never did. At this moment, it continues traveling outward, climbing toward the most distant point of its immense orbit. Every passing year carries it farther from the Sun, meaning any spacecraft launched from Earth would spend decades pursuing a destination that keeps retreating into deeper space. You are not simply aiming for where Sedna is today. You must predict where it will be several decades from now. Orbital calculations suggest that the most favorable opportunity arrives between about 2033 and 2046. During that period, a carefully planned gravity assist from Jupiter could dramatically increase a spacecraft's speed without requiring impossible amounts of fuel. Gravity assist means borrowing a small portion of a planet's orbital energy, allowing the spacecraft to leave the encounter moving much faster than it arrived. Missing that opportunity would likely demand either a far longer voyage or an entirely different form of propulsion. If such a mission launched during that favorable interval, it could reach Sedna in the late 2060s or the early 2070s. By then, Sedna would still remain near its closest approach to the Sun, resting roughly 85 to 87 astronomical units away. Even after traveling for decades, the spacecraft would have only hours, or perhaps a few days, to perform its closest observations before continuing onward into the darkness beyond. Entering orbit would remain beyond practical reach. The enormous speeds required to cross such distances leave too little opportunity for a spacecraft to slow down around a body with Sedna's modest gravity. Instead, the encounter would resemble the swift passage of New Horizons past Pluto, gathering every possible measurement during one precious flyby before the target gradually disappeared behind it. What could we gain from those fleeting moments? Detailed maps of Sedna's surface composition could reveal how its frozen chemistry varies from place to place. High resolution images might uncover craters, ridges, or other ancient landforms never before seen. Precise measurements of its gravitational pull could reveal the structure hidden beneath the surface, while sensitive cameras could finally settle the long standing question of whether a tiny companion moon has escaped detection. For a world that has remained preserved since the earliest days of the solar system, even a brief visit could transform decades of careful inference into direct exploration. Sometimes, the greatest challenge to an established scientific idea arrives in the form of a single distant world. Sedna occupies exactly that role. Its existence is more than an astronomical curiosity. It serves as a demanding test for every serious attempt to explain how our solar system came into being. Any model describing our origins must eventually account for Sedna's remarkable orbit. If it cannot, then some part of that history remains unfinished. One of the most influential explanations for the early evolution of our planetary neighborhood is known as the Nice model, named after the French city where it was first developed. This framework proposes that Jupiter, Saturn, Uranus, and Neptune did not always circle the Sun where we find them today. Instead, the giant planets gradually migrated through the young solar system, their enormous gravity scattering countless smaller bodies into new destinations and reshaping the architecture we observe today. The NICE model successfully reproduces many familiar features. It offers convincing explanations for the structure of the Kuiper belt and the existence of the distant Oort cloud. It also describes how migrating giant planets could rearrange vast populations of icy objects while preserving the overall stability of the planetary system. Across many computer simulations, the model repeatedly recreates patterns that closely resemble the solar system we know. But Sedna refuses to fit comfortably within that picture. Its closest approach to the Sun remains far beyond Neptune's gravitational reach. During the migration envisioned by the NICE model, Neptune could scatter nearby objects outward, yet it cannot naturally leave a body like Sedna, stranded with such a distant, closest approach, while remaining securely bound to the Sunday. The mathematics consistently points toward the same conclusion. Something appears to be missing. That leaves astronomers with only a handful of broad possibilities. Perhaps Sedna somehow reached its present orbit after the migration of the giant planets had largely concluded, although the timing makes that explanation difficult to support. Perhaps an outside influence, such as a passing star or an undiscovered massive planet, reshaped its orbit long after the planets settled into their present arrangement. Or perhaps the nice model itself captures only part of a more complicated story that scientists have yet to uncover. You might wonder how one distant object can influence an entire theory. The answer lies in the remarkable precision of modern orbital measurements. Every completed revolution, every closest approach, and every distant turning point preserves clues about the forces that acted billions of years ago. By comparing those measured paths with detailed simulations, astronomers perform a kind of celestial archaeology, reconstructing ancient events from the motions that survive today. If the passing star explanation eventually proves correct, Sedna would preserve evidence from the Sun's earliest home. Independent studies suggest that stellar birth clusters commonly disperse about 100 million years after their stars form. Sedna's orbit agrees remarkably well with that timescale, implying that our Sun may have spent roughly that long among countless neighboring stars before drifting into the quieter region of the Milky Way where we find ourselves today. In that sense, Sedna is more than a remote world. It is a surviving witness to the environment that shaped the beginning of our own cosmic story. Definitions in science often appear permanent until a new discovery quietly reveals their limits. Sedna occupies exactly that kind of boundary. Its orbit does more than challenge theories of planetary formation. It also raises an unexpectedly difficult question about how we decide what should and should not be called a planet. During August of 2006, the International Astronomical Union adopted three criteria for full planetary status. A planet must orbit the Sunday. It must possess enough mass for its own gravity to pull it into a roughly spherical shape. Finally, it must have cleared the neighborhood around its orbit, meaning it has become the dominant gravitational presence within its orbital region, rather than sharing that space with numerous comparable objects. Sedna satisfies the first requirement without question. It has circled the Sun since the earliest history of our solar system. Evidence also strongly suggests that its gravity has shaped it into a rounded world, rather than leaving it as an irregular fragment. The uncertainty emerges with the third criterion. Sedna travels along an orbit stretching from roughly 76 to more than 900 astronomical units from the Sunday. At such extraordinary distances, the idea of a clearly defined orbital neighborhood becomes much less straightforward than it is for the familiar planets closer to home. The International Astronomical Union also created the category of dwarf planet for worlds that satisfy the first two conditions while failing the third. Sedna almost certainly belongs within that description. Yet, the organization has never formally voted to recognize it as a dwarf planet. That absence of an official decision reflects uncertainty rather than disagreement over its physical nature. Part of the hesitation comes from Sedna's surroundings. You cannot easily classify a population when only a handful of its members have been discovered. Before Sedna appeared, astronomers had scarcely recognized the region between the Kuiper belt and the distant Oort cloud as a distinct part of the solar system. As additional worlds gradually emerge from that vast frontier, the broader context needed for classification is slowly taking shape. Mike Brown, whose discoveries helped reshape modern planetary science, has long argued that Sedna should be regarded as a dwarf planet in practical terms. Its estimated size and likely spherical form fit comfortably within that group. From his perspective, the absence of a formal vote changes very little about the object itself. Nature does not alter its characteristics because human terminology remains unfinished. You might wonder whether Sedna's classification will ultimately depend upon Sedna at all. The answer may well be no. The Vera C. Rubin Observatory is expected to uncover many additional members of this distant population during the coming years. As astronomers compare their sizes, orbits, and physical properties, the boundaries of this category should become much clearer. Such revisions are a familiar part of planetary science. Every generation of observations expands the map, and every expanded map encourages better definitions. Sedna reminds us that discovery often arrives first, while language follows carefully behind, adapting to a universe that continues to reveal far more variety than earlier generations ever imagined. Seen together, the distant worlds discovered during the early years of the 21st century resemble pieces of a steadily expanding map. Each new object pushed the known boundaries of the solar system a little farther outward. Each one revealed that the broad darkness beyond Neptune was far richer than earlier generations of astronomers had imagined. Yet, among all of these remarkable discoveries, one world continues to stand apart for reasons that extend well beyond its distance. During 2005, Mike Brown and his colleagues announced the discovery of Eris. Although Eris is slightly smaller than Pluto in diameter, it contains more mass, making it the most massive known dwarf planet. Its orbit carries it between roughly 38 and 97 astronomical units from the Sun, an impressive journey that still remains within a region where Neptune's gravitational influence provides a convincing explanation for its present path. Other discoveries soon followed. Quao R, Make, Haumea, and Gong Gong gradually transformed our understanding of the outer solar system. Each possesses its own distinctive characteristics, from unusual shapes to unexpected moons and complex surface chemistry. Together, they demonstrated that the Kuiper Belt contains numerous substantial worlds rather than scattered leftovers of planetary formation. The picture that emerged was one of remarkable diversity rather than emptiness. As this growing family of distant objects took shape, astronomers recognized an important pattern. Despite their differences, nearly every large body beyond Neptune approaches the Sun closely enough for Neptune's gravity to have influenced its orbit sometime during the history of the solar system. Orbital calculations can reproduce those paths with reasonable confidence using the migration of the giant planets and the long gravitational interactions that followed. Sedna refuses to fit into that pattern. Its closest approach to the Sun remains so distant that Neptune cannot plausibly account for its trajectory. That single fact separates Sedna from every other large object discovered in the same surveys. Instead of extending an existing category, it created an entirely new problem, one that reaches beyond planetary classification into the earliest history of the solar system itself. Because additional objects with similarly detached orbits have since been identified, researchers sometimes use the informal term sednoids to describe this unusual population. The name refers to extreme trans-Neptunian objects whose closest approaches remain beyond roughly 50 astronomical units, placing them in a remarkably isolated, dynamical environment. Among the confirmed members, Sedna and the object designated 2012 Victor Papa 113 remain the best studied examples. You can trace the birth of an entire scientific specialty to that realization. Before the night Sedna was detected, there was no dedicated field devoted to understanding these detached worlds. Today, planetary scientists investigate sednoids as a distinct population, comparing their orbits, compositions, and histories in search of clues about events that shaped the young solar system. A single discovery did more than add another object to a catalog. It opened an entirely new chapter in planetary science, one still being written as each additional distant world slowly comes into view. Long before any telescope forms an image of Sedna, an extraordinary journey has already unfolded across the solar system. The information reaching us begins as sunlight leaving the sun, crossing the immense gulf to a distant, frozen world, reflecting from its surface, then returning across that same gulf before finally arriving at a detector on Earth. By the time you see Sedna in an observatory image, the light has completed a voyage lasting roughly 23 hours, carrying with it one of the faintest messages astronomers can study. That remarkable delay means every observation is already part of history. We never witness Sedna exactly as it exists in the present moment. Instead, we see the world as it appeared nearly 1 day earlier. Compared with the age of the solar system, such a delay is insignificant. Yet it reminds us that even nearby members of our cosmic neighborhood exist across distances where light itself requires many hours to travel. Brightness becomes another source of knowledge. Sedna does not reflect identical amounts of sunlight from every part of its surface. Slight differences in color, texture, and composition cause tiny variations in reflectivity, the fraction of incoming light that bounces back into space. As the world slowly turns, those subtle differences create a repeating pattern of brightening and dimming. By carefully measuring that pattern over many observations, astronomers determined that Sedna completes one rotation in approximately 10 Earth days, revealing its leisurely spin without ever resolving the world into a visible disk. Even the Hubble Space Telescope cannot show mountains, craters, or plains upon Sedna. At its present distance, the entire world spans less than approximately 0.02 arcseconds across the sky, far below the telescope's resolving power. Every exposure records only a single unresolved point of light. There is no visible globe, no discernible outline, only a tiny source whose properties must be decoded through careful analysis rather than direct inspection. The James Webb Space Telescope offers a different advantage. Its exceptional sensitivity to infrared wavelengths, a region of light beyond human vision where many frozen materials leave distinctive signatures, allows astronomers to study Sedna's reflected spectrum in greater detail. Those measurements may distinguish specific varieties of tholins and identify subtle differences among frozen methane, frozen nitrogen, frozen water, and other surface materials that remain difficult to separate with earlier instruments. When you gather every known fact about Sedna, a striking pattern emerges. Its orbit, diameter, rotation, color, temperature, and composition all originate from the careful study of light. No spacecraft has approached it. No instrument has sampled its surface. No radio transmission has reached and returned from that distant world. Everything we understand comes from countless individual photons, each carrying a minute fragment of information across the darkness until, together, they reveal the portrait of a place that remains far beyond humanity's physical reach. Imagine the solar system before familiar worlds settled into the orderly paths we recognize today. The calm arrangement of planets had not yet emerged. Instead, the first several 100 million years were marked by relentless change as countless asteroids, icy bodies, and young planets crossed paths in a gravitational landscape that shifted from one age to the next. Sedna is one of the few surviving witnesses to that distant chapter, carrying within its orbit a record of events that no rock on Earth has preserved intact. Planetary scientists refer to part of this turbulent era as the Late Heavy Bombardment, a period that reached its conclusion approximately 3.8 billion years ago. Throughout that immense span, the inner solar system endured repeated impacts from asteroids and comets. Young planetary surfaces were reshaped again and again. Craters formed faster than erosion or volcanic activity could erase them, while the giant planets continued adjusting their positions through slow but powerful gravitational interactions. Jupiter drifted slightly inward. Saturn, Uranus, and Neptune gradually migrated outward. Those movements may seem modest compared with the enormous scale of the solar system, yet they dramatically altered the destinies of countless smaller objects. Every change in a giant planet's orbit redistributed gravitational energy, sending icy bodies toward the sun, casting others into distant space, and trapping some within long-lasting orbital resonances, regions where repeated gravitational patterns create stable pathways around the sunday. Many objects eventually settled inside the Kuiper belt because Neptune's gravity shepherded them into those resonances. Others received far stronger gravitational kicks, carrying them outward until they became members of the distant Oort cloud, where the sun's pull remains only barely sufficient to hold them. Sedna belongs to neither destination. Its orbit occupies an intermediate realm that existing models struggle to reproduce without invoking an additional influence, whether from a passing star, an undiscovered planet, or another process that has yet to be fully understood. As the bombardment gradually subsided, the solar system entered a more stable configuration. Planetary migration slowed. Major gravitational rearrangements became increasingly rare. The violence diminished, but its evidence never disappeared. Instead, those ancient events remained encoded within orbital paths that continued circling the sun exactly as celestial mechanics required. Sedna preserves one of the clearest examples of that enduring record. Its continued existence is remarkable in itself. A body traveling through such a distant region could easily have experienced further gravitational scattering over billions of years if its orbit had remained vulnerable. Instead, Sedna follows a stable path that appears to have been established very early in solar system history, and then left largely undisturbed across unimaginable stretches of time. When you examine Sedna's orbit, you are not merely tracing the motion of a remote icy world. You are reading a fossil preserved in gravity rather than stone, a lasting imprint from an era when the architecture of the solar system was still under construction, and when every passing encounter had the power to reshape the future of worlds that continue circling the sun today. Life almost certainly has no home on Sedna. The world is far too cold, sunlight far too weak, and liquid water entirely absent from its frozen surface. Every observation points toward an environment where familiar biological activity cannot begin or endure. Yet when astronomers discuss Sedna in the broader search for life, they do not dismiss it. Instead, they recognize that this distant world changes the question itself. Rather than asking where life exists, Sedna encourages us to ask where the ingredients of life are being assembled. Its surface contains tholins, complex organic molecules created when energetic radiation continually strikes simple frozen compounds such as methane and nitrogen. Over immense spans of time, those incoming particles rearrange atoms into increasingly elaborate molecular structures. The process requires neither biology nor a warm environment. It unfolds naturally across one of the coldest known landscapes in the solar system. These organic materials are not merely dark coatings upon ancient ice. They consist of carbon, hydrogen, nitrogen, and oxygen linked together into chains and rings of increasing complexity. Every passing age contributes another tiny step in that gradual chemical evolution. Sedna has preserved the results of this process for billions of years, offering a rare opportunity to study chemistry that has remained largely untouched since the earliest history of the solar system. Laboratory experiments have made those discoveries even more compelling. Scientists have produced tholins under carefully controlled conditions that simulate the radiation and frozen gases found in deep space. When those laboratory samples are later mixed with liquid water, they naturally generate amino acids, the molecular building blocks of proteins, along with nucleobases, the essential components from which ribonucleic acid and deoxyribonucleic acid are constructed. These experiments do not create living organisms, yet they demonstrate that remarkably sophisticated chemistry can emerge long before biology ever appears. You should not interpret those results as evidence that life exists on Sedna. Nothing currently suggests such a possibility. Instead, they reveal that the chemical foundation from which life may eventually arise is widespread rather than exceptional. Similar radiation driven reactions are expected to occur across countless icy worlds orbiting distant stars, wherever frozen carbon rich materials remain exposed for immense periods of time. Seen from that perspective, Sedna becomes one chapter in a much larger cosmic story. Earth did not invent the chemistry that supports living systems. The young planet inherited many of its raw materials from the ancient molecular cloud that collapsed to form the Sun approximately 4.6 billion years ago. Sedna has preserved part of that inheritance in an environment that changed remarkably little, while Earth experienced oceans, continents, and evolving life. A future mission capable of returning even a few grams of Sedna's reddish surface material would provide an extraordinary scientific treasure. Those frozen organic compounds could represent one of the most pristine collections of prebiotic chemistry ever examined, preserving molecular processes that began before our planet became the living world we know today. There are moments in astronomy that last far longer than a human lifetime, yet remain astonishingly brief when measured against the motions of the solar system. We happen to live during one of those rare intervals. As you look toward Sedna through the discoveries of modern science, you are witnessing a world passing through the only favorable chapter our civilization will ever know. Current orbital calculations place Sedna near its perihelion, the closest point in its immense journey around the Sunday. That closest approach occurs around the years 2075 and 2076. Even now, the distant world remains within only a few astronomical units of that turning point, making it brighter and more accessible than it will be for thousands of years to come. The previous perihelion unfolded around 9400 before the Common Era. Humanity had not yet developed agriculture. Permanent cities had not appeared. Writing, mathematics, and recorded history still belonged to the distant future. No observer could have recognized the faint reddish point crossing the outer darkness. The opportunity simply passed unnoticed beneath skies that belonged to an entirely different world. After this passage, Sedna will not return until approximately the year 13,400 of the Common Era. By then, every nation, language, and institution familiar to us today may exist only as fragments of history, if they survive at all. The interval between those two encounters spans nearly the whole arc of recorded civilization. That perspective transforms an ordinary astronomical observation into something remarkably uncommon. Every telescope ever constructed, from modest observatory instruments to the Hubble Space Telescope and the James Webb Space Telescope, has operated during this single favorable approach. Every photograph, every spectrum, every refined orbital calculation belongs to the same fleeting window. We did not simply discover Sedna. We encountered it during the only period when discovery was realistically possible. The timing extends beyond observation. Mission studies indicate that the most practical opportunity for a flyby using current propulsion methods falls between approximately the years 2033 and 2046. During that interval, a carefully planned gravity assist from Jupiter could send a spacecraft outward quickly enough to intercept Sedna while it still remains comparatively nearby. Each passing year gradually shifts the geometry against us. Once Sedna continues its long retreat toward aphelion, the farthest point of its orbit, every future mission becomes more demanding. Travel times lengthen, energy requirements increase. Scientific opportunities become progressively harder to seize. Orbital mechanics, the mathematics describing how gravity shapes motion through space, offers no shortcuts and no second chances. Whether humanity ultimately launches such a mission remains uncertain, yet the decision itself belongs almost entirely to our generation and the few that immediately follow. If we choose to act, we will meet a survivor from the dawn of the solar system. If we do not, the opportunity will drift outward with Sedna, remaining beyond practical reach until another civilization, under another sky, witnesses its distant return more than 11,000 years from now. Long before we identified Sedna, the forces capable of shaping its orbit were already understood as natural consequences of star formation. Every young planetary system begins its existence surrounded by neighboring stars. You can imagine those crowded stellar nurseries as places where gravity reaches far beyond the boundaries of any single newborn sun, gently reshaping worlds before they have settled into the patterns we later mistake for permanence. Astronomers now believe that nearly every star is born within a stellar cluster, a temporary gathering containing hundreds or even thousands of young stars. During the first tens of millions of years, close stellar flybys occur often enough to influence the distant outskirts of developing planetary systems. Such encounters need not be catastrophic. A passing star can slightly alter the paths of remote icy bodies, leaving behind populations of objects whose unusual orbits remain as evidence billions of years later. From that perspective, Sedna may represent something far larger than an isolated curiosity. It could be one member of a class of distant survivors created whenever neighboring stars briefly exchanged gravitational influence during their youth. If that picture proves correct, countless planetary systems scattered across the Milky Way may possess their own distant populations of Sedna-like worlds, circling far beyond the regions where ordinary planets reside. For now, those distant counterparts remain beyond our reach. Objects this small and faint cannot be observed directly across interstellar distances with present technology. Yet astronomers can still search for indirect clues. By studying the orbital architecture of planets, debris disks, and smaller bodies around other stars, researchers can reconstruct the gravitational history of those systems, much as archaeologists reconstruct vanished civilizations from scattered remains. The evidence lies within motion itself. Another possibility leads to an equally fascinating conclusion. If an undiscovered massive planet, commonly known as Planet 9, eventually explains Sedna's orbit, then our solar system may resemble many others more closely than once believed. Space telescopes, such as the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, have revealed that planets larger than Earth, but smaller than Neptune, appear remarkably common around distant stars. These worlds, often called super-Earths, occupy a category our own planetary family seem to lack. That apparent absence has always been something of a puzzle. But if Planet 9 truly exists in the remote outskirts beyond Neptune, then our solar system may possess such a planet after all. It would simply travel so far from the Sun that only its subtle gravitational influence betrays its presence. Sedna reminds us that scientific certainty is never fixed. Each discovery expands the map while revealing how much remains outside it. As we continue exploring the outer frontier of our own solar system, you begin to see that every unexpected orbit carries a broader message. The history of one distant world can reshape how we imagine planetary systems throughout the galaxy, encouraging us to treat every established model as a careful draft rather than a finished story. Scientific discoveries are often remembered by the names attached to them, yet each name represents years of patient observation, failed searches, careful calculations, and an enduring willingness to question accepted ideas. As we follow Sedna's story, you also encounter the researchers whose persistence gradually revealed that the outer reaches of the solar system were far richer than almost anyone expected. Mike Brown devoted much of his career to a systematic search for large bodies beyond Neptune, using increasingly powerful telescopes and software designed to recognize the faintest moving points against crowded star fields. His work reshaped planetary science repeatedly, but Sedna remains perhaps his most disruptive discovery. Although many people later associated Brown with Pluto's reclassification, Sedna challenged scientific thinking in an even deeper way by exposing an entirely new dynamical region beyond the familiar boundaries of the Kuiper Belt. The search did not end there. Chad Trujillo, who helped discover Sedna, continued exploring the distant frontier alongside Scott Shepard. Their observations eventually led to the identification of another remarkable world, designated 2012 Victor Papa 113. Informally nicknamed Biden, this object demonstrated that Sedna was not an isolated oddity. Instead, it belonged to a broader population occupying similarly detached orbits, strengthening the case that the inner Oort cloud represented a genuine structure rather than a statistical accident. Those discoveries inspired an entirely new line of investigation. In 2014, Trujillo and Shepard published research noting that several extreme trans-Neptunian objects appeared to share unusual orbital alignments. A trans-Neptunian object is simply any body whose average distance from the Sun lies beyond Neptune. The pattern hinted that an unseen source of gravity might be shaping these distant paths, introducing the idea that a massive undiscovered planet could still be waiting in the darkness. Scott Shepard has continued expanding that catalog through extensive observing campaigns at the Carnegie Institution for Science. Year after year, his surveys have uncovered additional extreme trans-Neptunian objects, providing the measurements that keep this debate grounded in observation rather than speculation. Every newly measured orbit adds another piece to an increasingly detailed portrait of the solar system's distant architecture. The theoretical side of the investigation has advanced alongside the observations. Konstantin Batygin, working with Mike Brown at the California Institute of Technology, developed sophisticated numerical models exploring whether a distant, massive planet could naturally reproduce the orbital patterns astronomers were measuring. These simulations, computer calculations that follow the gravitational interactions of many bodies over immense spans of time, suggested that random chance alone was an unlikely explanation. Badigan has estimated the probability of the observed clustering arising by coincidence at less than one chance in 500. Perhaps the most remarkable aspect of this story is its timing. Barely 3 decades ago, the instruments needed to detect worlds like Sedna did not exist. The questions guiding today's research had not yet been imagined because the evidence itself remained hidden. You are watching planetary science evolve in real time as each new discovery redraws the map and reveals that the solar system still holds territories waiting to be understood. Imagine setting aside every map of the solar system you have ever seen. For generations, those diagrams suggested a tidy arrangement, with familiar planets fading into the Kuiper belt before the darkness truly began. Sedna asked astronomers to unfold that map once again, revealing that the territory beyond Neptune was far larger than anyone had confidently measured. Before Sedna entered the scientific record, the practical frontier of the known solar system extended to roughly 50 astronomical units from the Sunday. Beyond that distance, observations grew sparse, and the Kuiper belt appeared to mark the outer limit of a well understood population of icy bodies. Sedna transformed that picture immediately. Although it currently travels near its closest approach, its elongated orbit eventually carries it outward to approximately 936 astronomical units, extending the known reach of the Sun's gravitational family by an extraordinary margin. Later discoveries strengthened that expanding view. The identification of 2012 Victor Papa 113 demonstrated that Sedna was not alone in occupying this detached realm. Meanwhile, the Planet 9 hypothesis suggested that an undiscovered massive world could be orbiting hundreds of astronomical units from the Sun, perhaps near 800 astronomical units. Whether that planet ultimately exists or not, the search itself reflects how dramatically our understanding has changed within only a few decades. The scale grows even more astonishing beyond these distant objects. The theorized Oort cloud, believed to be the vast reservoir supplying many long-period comets, may extend outward to nearly 100,000 astronomical units. At that immense distance, the outermost members remain only weakly bound to the Sunday. Expressed another way, the cloud could stretch almost 1 6/10 light years into space. The nearest known star, Proxima Centauri, lies approximately 4 and 24 hundredths light years away. Our solar system, if the Oort cloud truly surrounds it as expected, reaches nearly halfway toward another star before gradually fading into interstellar space. That realization changes how we define a boundary. There is no sharp edge where the solar system simply ends. Instead, the influence of the Sun weakens across an immense gradient spanning trillions of miles, blending almost imperceptibly into the wider galaxy. The transition resembles a shoreline disappearing beneath an incoming tide, rather than a wall separating one region from another. Voyager 1 illustrates that scale with remarkable clarity. In August of 2012, the spacecraft crossed the heliopause, the region where the outward pressure of the solar wind yields to the surrounding interstellar medium, at a distance of approximately 121 astronomical units. Traveling away from the Sun at roughly 38,000 miles per hour, Voyager 1 will still require about 300 years to reach the inner Oort cloud. Crossing that enormous region may demand another 30,000 years. Against such distances, Sedna occupies an extraordinary place. You can think of it as a milestone marking where our familiar solar system begins dissolving into something vastly larger, a reminder that the map continues long after the planets have disappeared from view. Time moves differently in the outer solar system. While civilizations rise and vanish within a few thousand years, Sedna advances along its immense orbit with almost imperceptible patience. Even now, as we observe it near the closest part of its journey around the Sun, the direction of its travel has already changed. With each passing century, it will slip farther into the darkness, beginning a return voyage that will continue long after our own era has become distant history. The first stages of that retreat unfold gradually. Over many generations, the change would barely be noticeable without precise measurements, yet the distance continues to grow. By the year 3000 of the Common Era, Sedna is expected to lie near 200 astronomical units from the Sun, roughly twice its present distance. By the year 5000, it may reach approximately 400 astronomical units. Around the year 8000, it approaches 700 astronomical units, and by the year 12,000, it nears the farthest point of its orbit, approximately 936 astronomical units from the Sunday. At that extraordinary distance, the familiar dominance of the Sun begins to fade. Sedna still remains gravitationally bound to our star, yet the bond becomes increasingly delicate. The surrounding galaxy, normally so distant that its influence can be ignored, begins to contribute measurable effects. Astronomers describe one of these influences as the galactic tide, the gentle but persistent gravitational pull created by the combined mass of the Milky Way. It acts across enormous distances, subtly reshaping the paths of the most remote objects surrounding the Sunday. The galactic tide is believed to play an important role in the distant Oort cloud. Over spans of millions of years, its influence can disturb icy bodies resting at the edge of the Sun's domain, nudging some of them inward until they eventually appear as long-period comets crossing the inner solar system. Sedna does not travel quite far enough for this effect to dominate its orbit on timescales meaningful to humanity. Even at aphelion, the Sun remains the principal architect of its path, yet the galaxy begins to make its presence known, reminding us that no planetary system exists in complete isolation. That realization gives Sedna's future an unusual perspective. As the world drifts outward, it enters a realm where the boundaries between our solar system and the broader Milky Way become increasingly subtle. Gravity from our own star still guides the journey, but the larger structure of the galaxy provides a faint background influence, almost like an unseen current beneath a vast ocean. When Sedna finally returns to perihelion, roughly 11,400 years from now, the observers waiting beneath Earth's sky may know nothing of the work accomplished today. Languages will have changed. Cultures will have transformed beyond recognition. Unless some enduring record survives the passage of time, they may discover Sedna anew, unaware that another civilization once measured its orbit, debated its origin, and wondered what stories could be written from a single distant world moving patiently through the deep frontier of the Sunday. Sometimes the greatest discoveries begin with almost nothing at all. In Sedna's case, the first clue was a faint point of light drifting so slowly across the background stars that it could easily have been overlooked. A careful observing team, patient analysis, and software designed to notice tiny motions combined at exactly the right moment. What appeared at first to be another distant object soon became something far more significant. Its orbit refused to fit the picture astronomers believed they understood. That pattern appears again and again throughout the history of astronomy. Many of the discoveries that reshape science are not the ones researchers set out to find. Instead, they arrive unexpectedly, asking questions nobody realized needed answers. Predictions remain essential. Yet the universe often advances our understanding by presenting evidence that refuses to cooperate with familiar ideas. You can trace that tradition across centuries of exploration. In the year 1781, William Herschel was carefully surveying stars when he noticed an object that slowly changed position. It became Uranus, the first planet discovered in modern times. Neptune followed a different path. During the year 1846, mathematicians calculated where an unseen world should be, based on subtle disturbances in Uranus's orbit. Telescopes then confirmed the prediction with remarkable precision. Even afterward, Neptune continued revealing unexpected behavior through the motions of its moons, reminding astronomers that one solved mystery often leads to several new ones. Pluto added another chapter. Discovered in the year 1930, it emerged during the search for a much larger world, sometimes called Planet X. Yet Pluto proved far too small to account for the gravitational effects astronomers expected. The original prediction failed, but the search still uncovered an entirely new member of the solar system. Discovery had arrived by a route nobody anticipated. Sedna carried that tradition into the 21st century with unusual force. It was not merely another icy body beyond Neptune. Its orbit revealed a region that had not been recognized before, one lying between the familiar Kuiper belt and the immense Oort cloud. Suddenly, the outer solar system became larger, more complicated, and considerably less settled than textbooks had suggested. Existing theories could explain much of what had already been observed, yet Sedna insisted that something important remained missing. Every major discovery leaves behind more than an additional entry in a catalog. It redraws the framework used to interpret everything around it. Sedna accomplished exactly that. A single distant world inspired new ideas about stellar encounters, unseen planets, and the earliest history of the sun's birthplace. Could one faint object truly reshape decades of planetary science? Its enduring influence suggests that the answer is yes. Science grows through this continuing conversation with the unexpected. Each surprising observation tests accepted explanations, exposes hidden assumptions, and encourages better ones to take their place. Sedna stands as one of the clearest modern examples of that process, a reminder that the universe still holds discoveries capable of changing not only what we know, but also how we learn. There is a remarkable honesty at the heart of Sedna's story. After more than 2 decades of observation, careful calculations, and increasingly sophisticated instruments, the catalog of unanswered questions remains longer than the list of established facts. That is an unusual position for an object studied by astronomers around the world. Yet it is precisely where Sedna continues to stand, inviting investigation while resisting simple explanation. We still do not know what placed Sedna into its extraordinary orbit. Competing ideas remain under active discussion, from an ancient encounter with another star to the gravitational influence of an undiscovered distant planet. Each possibility explains part of the evidence, yet none has earned universal acceptance. The path Sedna follows around the sun continues to preserve a chapter of history whose full meaning has not yet been translated. Other uncertainties reach inward. Does Sedna possess a small moon too faint for present observations to reveal? What minerals and frozen compounds truly cover its surface beyond the broad chemical signatures recorded by spectroscopy, the technique of separating light into its individual colors to identify matter? Beneath those ancient layers of ice, is there a differentiated interior, meaning heavier material settled toward the center while lighter material remained above? Every answer would reshape how we understand this remote world. Its place within the larger solar system remains equally uncertain. Is Sedna one example among thousands of similar bodies waiting to be discovered, or is it an exceptionally rare survivor of events that almost never occurred? Surveys continue to uncover additional distant objects, but the known population remains too small to settle that question. Even the existence of the proposed Planet 9 remains unresolved, despite years of detailed simulations and persistent searches across enormous regions of sky. These are not minor details left for specialists to debate. They are foundational questions about how our planetary neighborhood formed, how it evolved, and what forces shaped it during its earliest ages. A single confirmed answer could require scientists to revise long accepted ideas, just as previous discoveries have done throughout the history of astronomy. You might wonder whether uncertainty weakens science. In practice, the opposite is true. Scientific progress depends on recognizing the boundaries between evidence and assumption. Every unanswered question becomes a destination for better observations, more capable telescopes, and more complete theories. Confidence grows strongest when researchers identify exactly where their knowledge ends. Sedna reminds us that the universe is under no obligation to match human expectations or schedules. Even with the finest observatories ever constructed, some mysteries remain beyond our present reach. That persistence is not evidence that science has failed. It shows science working exactly as intended, measuring uncertainty with increasing precision, refining each question, and patiently preparing for the discoveries that future generations may finally bring into view. Every generation inherits a different horizon. Long ago, the edge of the known world was the far side of an ocean or the crest of an unfamiliar mountain. Explorers could eventually stand where they had once only imagined. The boundary always retreated as knowledge advanced. Today, our horizon lies far beyond any landscape you could cross on foot. It extends into the outer reaches of the solar system, where worlds like Sedna drift through distances that challenge ordinary imagination. For most of human history, every frontier remained, at least in principle, reachable within a lifetime. A determined traveler could sail to a distant shore, cross a continent, or circle the globe. Sedna belongs to a different category altogether. Even with the most capable spacecraft humanity has yet built, reaching this remote world would demand decades of travel. The people who conceived such a mission might never witness its arrival. Those who eventually receive its discoveries could belong to an entirely different generation. Yet we continue planning anyway. We have detected Sedna, calculated its orbit with remarkable precision, estimated its size, studied the sunlight reflected from its surface, debated its origin, and considered sending a robotic explorer across the immense gulf separating it from Earth. That willingness reveals something fundamental about scientific inquiry. We are prepared to invest years of effort into questions whose answers may arrive long after the original investigators are gone. Knowledge becomes a gift carried forward rather than a reward collected immediately. This perspective reaches beyond astronomy. Every observatory, every spacecraft, and every carefully preserved archive depends upon the assumption that future people will continue asking questions. Science becomes a conversation extending across generations, with each discovery building upon observations recorded by those who came before. Sedna represents one of the clearest examples of that enduring commitment. Its position also changes how we think about the edge of the solar system. Sedna feels distant because it rests near the limit of what present technology allows us to examine directly. But that impression comes from our perspective rather than from nature itself. Beyond Sedna stretches the inner Oort cloud, across hundreds of astronomical units. Farther still lies the outer Oort cloud, then the vast interstellar medium between the stars. Beyond that are the countless suns of the Milky Way, the neighboring galaxies of the local group, and, farther still, the observable universe containing trillions of galaxies. Seen against that immense backdrop, Sedna occupies a surprisingly nearby address. It belongs to our own cosmic neighborhood, orbiting the same sun that warms Earth. Even so, we have only begun to understand it. That contrast offers a lasting reminder of our place in the universe. The frontier before us is neither a wall nor an ending. It is simply the distance between what we have already learned and everything that still waits beyond the next discovery. Long before Earth had oceans or continents, before there was a moon bright enough to light a night sky, a vast molecular cloud began collapsing beneath its own gravity. Over millions of years, the growing mass at its center ignited into the sunday. Around it, a broad disk of gas, dust, ice, and rock slowly gathered into countless new worlds. From that same shared beginning emerged the planets, the asteroids, the comets, the distant Oort cloud, and one small frozen world we now call Sedna. That common origin connects places separated by astonishing distances. The atoms within your body, the mountains rising above Earth's surface, the water filling its oceans, and the ancient ice resting upon Sedna all trace their history to the same stellar nursery. Their differences were shaped afterward through temperature, gravity, sunlight, chemistry, and time. A change in circumstance transformed one collection of material into a living planet, while another drifted into the deep outskirts of the solar system, preserving conditions that have scarcely changed for billions of years. During Earth's long biological story, Sedna has remained an almost motionless witness. The first simple animals appeared. Fish filled ancient seas. Forests spread across continents. Dinosaurs rose and vanished. Ice ages came and went. Human civilization emerged in only the briefest instant of geological time. Across all those ages, Sedna completed less than half of a single journey around the Sunday. Its immense orbit compresses the whole history of complex life on Earth into only a fraction of one celestial year. The scale grows even greater when we extend our view farther into the future. Long after humanity's present era has become unimaginably distant, the sun will exhaust the hydrogen sustaining its core. It will expand into a red giant, transforming the inner solar system forever. By then, the familiar conditions that shaped Earth will have disappeared. Against that immense timeline, whether we launched a spacecraft towards Sedna may seem like a remarkably small event. Yet the desire to consider such a mission carries a significance that cannot be measured only in years or miles. It reflects something distinctive about our species. We build telescopes to examine worlds we cannot visit. We send robotic explorers, knowing they may return discoveries for people we will never meet. We preserve observations so future generations can continue questions that began before they were born. Curiosity reaches farther than any spacecraft. Sedna itself asks for none of this. It has circled the sun through billions of years without announcing its presence, waiting beyond the familiar planets in enduring darkness and enduring cold. We are the ones who searched until we found it. We are the ones who recognized that a faint point of light could change the story of our solar system. In the end, Sedna's greatest lesson may not be about a distant world at all. It may be about the enduring human instinct to look beyond every known horizon and keep looking.